We have now encountered several versions of the Fourier transform for sequences, finite lengths and infinite lengths, namely the discrete Fourier transform for finite length sequences, the discrete Fourier series for periodic infinite length sequences, and finally the discrete time Fourier transform, or DTFT, for infinite length sequences. How do these various forms of the Fourier transform interact with each other? So first we're going to look at how to compute the DTFT of a periodic sequence. That will involve the delta function again. And we are also going to see how to compute the DTFT of a finite length sequence and how it relates to the DFT of that finite length sequence. At the end, we're going to look at a technique called zero padding, which is a way to interpolate the spectrum of a finite length signal using a DFT of a longer signal which has zero appended to the initial signal. So that's a technique that very often used to display spectra, and so it's important to understand how it functions. Module 4.7 Relationships between transforms. We have seen the discrete Fourier transform, the discrete Fourier series, as well as the discrete time Fourier transform. Now we are going to look at the DTFT of periodic sequences on the one hand and the DTFT of finite support sequences, and create a relationship between these two cases and the DFT or DFS. Finally, we will look at zero padding, techniques that is often used to smooth spectra from finite length signals. The DFT and the DFS can be seen as changes of basis in C capital N. It's obvious because it's a matrix vector multiplication, and we go from the original domain to the DFT domain. The DTFT, on the other hand, we introduced as a quote-unquote formal change of basis over L2 of Z, the space of finite energy sequences. The basis vectors are building blocks for any signal, so we can write a signal as a linear combination of basis vectors. In the case of the DTFT, this is formal because the index for the DTFT, which is frequency omega, is uncountable, so we don't have a countable basis, yet the intuition we have from the DFT or the DFS carries over in that sense to the DTFT, as we have seen in the preceding submodule. The DFT and the DTFT are really two sides of the same coin. The DFT leads to numerical algorithms, it's essentially linear algebra, and we can derive fast algorithms based on this formalism. The DTFT is more of a mathematical tool. It comes in handy when we want to make proofs and to see properties of Fourier transforms. If we are given a finite length signal xn, which has capital N non-zero entries, say for n goes from 0 to capital N minus 1. Then the natural spectral representation, as we have seen, is a DFT given by capital X of k. Now there are two ways to embed xn into an infinite sequence. One is we can do a periodic extension, so we take the index modulo capital N, that gives us x tilde of n, which is simply the repetition where the period is of length capital N. Another way is a finite support extension, so we denote this by x over bar, which is equal to xn on the interval 0 to capital N minus 1 and equal to 0 otherwise. How does xk, the DFT of the finite length signal, relate to the DTFT of these two forms of signals? This is what we shall pursue in the next few slides. So what is the DTFT of x tilde of n? Well, it's capital X tilde of e to the j omega, which is a formal power series of x tilde of n multiplied by e to the minus j omega n. In this expression, we replace x tilde of n as the inverse Fourier series of capital X tilde. It's in the expression between parentheses. This, of course, is equal to the inverse DFT, and we simply reorder the sums. So we take out the sum over k in front, and we leave inside the parentheses the sum over n, gathering the e to the j to the various power terms. Then we recall that this infinite sum of e to the j 2 pi over n and k times e to the minus j omega n is simply the DTFT of a complex exponential of frequency 2 pi over capital N times nk. And this, we know, is going to be our delta tilde signal shifted to the location 2 pi over capital N times k. With this, we have now a formal expression for x tilde of e to the j omega, namely it's 1 over n, the sum of the DFT coefficients, capital Xk, multiplied by delta tilde shifted to the frequency 2 pi over capital N times k. Let us look at an example and take a good old friend, the 32-tap sawtooth sequence. We remember also the DFT of this 32-tap sawtooth. The periodic sawtooth sequence is shown in this figure for a few periods. The DTFT of the periodic extension now is this weighted set of Diracs, so the Diracs sit at multiples of 2 pi over capital N, and they are weighted by capital X of k. So characteristically at the frequency 0, it's equal to 0, because the sawtooth sequence has an average of 0, and then it has the shapes that we know from the DFT of the sawtooth sequence. To recap, this spectrum looks exactly like capital X of k, except that the display is different because the 0 frequency is at the center rather than at the left end, and we have a 2 pi periodic spectrum where we only show the spectrum between minus pi and pi, and of course, rather than having finite values capital Xk, we have deltas, as is indicated here with the red arrows. Let us do the very same exercise, but now with a finite support signal. So x over bar, as we indicated, is equal to xn over the interval 0 to capital N minus 1, 0 otherwise. The DTFT, denoted by x over bar e to the j omega, is simply the sum of x over bar times e to the minus j omega n, which in this case is a finite sum because xn is 0 elsewhere. So it's a sum from 0 to capital N minus 1 of e to the minus j omega n. Now this looks very much like the DFT, except we don't have k. In the exponent we have omega. Okay, on the second line of this development, we can replace x over bar by the inverse DFT of capital Xk, so which is written between parentheses. Then we can take the sum over k outside with the x capital K, and within the parentheses we simply have the complex exponentials, and the exponent now is omega minus 2 pi over capital N times k multiplied by n. The key is therefore this expression between parentheses, this finite sum with the exponent omega minus 2 pi over n times k, and this we denote by r over bar with the shift to the location omega minus 2 pi over capital N times k. This r over bar is actually the DTFT of the interval indicator signal, so the interval indicator is 0 elsewhere but on the interval 0 to capital N minus 1. So we show here r over bar, simply in the case of n is equal to, well, let's count, must be 9 or something like this in this case here. Very simple elementary signal, and we're going to calculate the DTFT of this r over bar signal. So r over bar e to the j omega, it's a sum of e to the minus j omega n from 0 to capital N minus 1. This is our good old friend, it's a finite geometric series. We see this on the second line. We take out a phase factor, e to the minus j omega capital N over 2, both upstairs and downstairs, but downstairs without the capital N. And this allows us to replace what's between square brackets as sine of omega n over 2 versus in the denominator sine of omega over 2, and the phase factor is simply factored out. We see now the DTFT for the case n is equal to 9, and in this case we show the real part, and if we center actually this signals, and the phase factor would be equal to 1, and we see exactly this. Now we can finish the computation of the DTFT of a finite support signal. So x over bar of e to the j omega is the sum from 0 to capital N minus 1 of xk times lambda omega minus 2 pi over n times k, where lambda of omega is simply a renormalized version of r over bar, the DTFT of the finite interval indicator signal. Let us look at what happens if we take the 32-tap sawtooth sequence. We know the DFT, an old friend. It must be the third time that we see this DFT with a zero value at the origin 0 and its characteristic decay and then going back up towards 31. The finite support extension is shown here for a support of, I guess, 128, plus minus 128. So we see the sawtooth in the middle and it's 0 elsewhere. The DTFT of the finite support extension is now sketched here by taking the DFT and smoothing it by interpolating with the R of e to the j omega function. So we add 1, 2, 3, etc. And as we go, we find the smooth interpolation here between the points of the DFT that are in light gray in the background. This should look familiar because we have computed this spectrum already once in module 4.4 and we got the exact same result. As a comparison to the DTFT of the periodic extension, we see some similarity but some differences. So here we have a smooth spectrum. In the case of the periodic extension, we had a set of Diracs, but of course they coincide at the location of the Dirac. We pass exactly through with the red function here, which is a smooth interpolation. Now, this was quite a bit of effort to actually compute the DTFT of a finite support signal. And so what people often do is that they take the finite support signal, they extend it with zeros, so-called zero padding, and then they compute the DFT numerically. It generates definitely nicer plots, and we shall see a few examples in the next slides. The DFT of the 32-tap sawtooth, again, and we are going to zero pad it. So here we zero pad it with 64 zeros, so the first 32 entries are equal to the sawtooth, and the next 64 entries are just zeros. You see the DFT, it has a similar shape as the DFT of the initial period of length 32. At the origin, at k is equal to 0, it's still 0, so no surprise there. So let us compute the discrete Fourier transform of a zero-padded signal. Let's call it capital Xm of h, where h is a frequency. It is the sum from 0 to capital M minus 1 of a signal x prime, which is the extension of the initial signal x, and the usual expression. So this is a sum from 0 to capital N minus 1 of xn, e to the minus j 2 pi over capital M, that's the important point, n times h. We do the usual trick. By now you should be familiar with this one. So we have the sum over small n, and then we replace xn by the inverse DFT of capital Xn in its usual expression, and we then reorder the summations. So we take out the summation over k in front with the x sub n k, and between parentheses we have this expression which now looks familiar. It's a sum from 0 to capital N minus 1, and it has exactly the same expression as the DTFT of a finite length signal, but instead of having omega we have 2 pi over capital M times h. And so this is simply the expression of x over bar e to the j omega evaluated at the location omega is equal to 2 pi over capital M times h, the exercise we had done before. So obviously zero padding does not add any information that is not already in the DFT or, for that matter, in the DTFT. And so a zero-padded DFT is simply a sampled version of the discrete time Fourier transform of the finite support extension of the signal. let us do this by example again. Guess what? We take the 32-tap sawtooth sequence, 0-padded, so the 32-point DFT we are familiar with, of course. Here is 1/2 of this 32-point DFT. And then we have the DTFT of the finite support signal in blue. And we simply sample it. For example, here we have the 96-point DFT, which was the extension we had seen just earlier. And we find indeed the DFT as predicted by sampling. We do the same exercise now with a 200-point DFT, and this is a sampling of the DTFT of the finite support signal, as shown here in blue and the samples in red.